Before Voyager reached the edge of our solar system, it had already done something almost impossible. It had crossed the orbits of worlds that ancient people could only see as wandering points of light. It had flown past Jupiter, a planet so large that more than 1,000 Earths could fit inside it. It had watched storms wider than continents. It had seen moons covered in ice, moons covered in volcanoes, moons that looked dead, and moons that suddenly seemed more alive than anyone expected. Then it kept going, past Saturn, past the last beautiful close-up images it would ever take, past the planets that gave it speed, past the region where sunlight still feels like a real source of warmth, and eventually, far beyond everything familiar, Voyager reached a place where the solar system no longer ended in the way most people imagine. There was no wall. There was no glowing line in space. There was no sign that said Earth was behind it and the galaxy was ahead. Instead, the spacecraft found a boundary made of invisible pressure, magnetic fields, charged particles, dying solar wind, and radiation from the rest of the Milky Way. And that is what makes this story so strange, because the edge of our solar system is not a place you would recognize with your eyes. It is something you have to feel with instruments. Before we begin, if you enjoy calm journeys through the deepest parts of space, take a second to subscribe, leave a like, and write in the comments where you are watching from and what time it is for you right now. Somewhere on Earth, someone may be watching this before sunrise, while someone else may be listening in the middle of the night, and that makes this journey feel even more connected. Tonight, you are watching the Just About Space channel, talking about what Voyager found 18 billion kilometers from Earth. And to understand what Voyager found out there, we have to begin with a simple idea that is much stranger than it sounds. The solar system is not just the planets. Most of us grow up imagining the solar system like a neat diagram in a school book. The sun sits in the center. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune orbit in clean circles around it. Maybe Pluto appears at the edge if the diagram is old enough, or if someone still likes to include it for emotional reasons. Beyond that, the picture usually fades into empty black space. But diagrams lie by being too clean. They make the solar system look like a collection of balls placed on a flat map. They show orbits as if the planets are sitting on invisible tracks. They shrink the distances so aggressively that Jupiter looks close to Mars and Neptune looks close to Uranus, when in reality, the spaces between them are enormous. And most importantly, they almost never show the thing that actually surrounds all of them. The sun is not just a glowing ball, it is also blowing itself outward. Every second, the sun releases a stream of charged particles called the solar wind. These particles are mostly protons and electrons, moving away from the sun in all directions. They are not bright like sunlight. You cannot see them with your eyes, but they fill interplanetary space with a kind of invisible atmosphere from the sun. This solar wind carries part of the sun's magnetic field with it. It expands through the solar system, flows around planets, pushes against magnetic fields, and creates a vast bubble around the sun called the heliosphere. That bubble is one of the most important things in this story, because when people say Voyager reached the edge of our solar system, they are often talking about the edge of the heliosphere, not the edge of the sun's gravity, not the edge of every object that orbits the sun, not the farthest frozen comet, but the boundary where the sun's outward flow finally loses its control. Inside the heliosphere, space is still shaped mostly by the sun. Outside it, the environment belongs more to the galaxy. The particles, the magnetic field, and the pressure come from interstellar space, the thin material between the stars. So the real question is not whether Voyager crossed a line drawn on a map. The real question is this: how far does the sun's influence reach before the galaxy pushes back? That question sounds simple, but it took humanity more than 35 years of flight to answer directly. Voyager was not originally built only to answer it. The mission began with a rare opportunity. In the late 1970s, the outer planets were arranged in a way that would not happen again for about 175 years. Jupiter, Saturn, Uranus, and Neptune were positioned so a spacecraft could use one planet's gravity to slingshot toward the next. This meant that one mission could potentially visit several giant worlds in a single journey, using gravity like a cosmic staircase. This was called the Grand Tour. The original dream was enormous. Send spacecraft outward, let Jupiter accelerate them, let Saturn bend their paths, and if everything worked, continue on to Uranus and Neptune. But dreams become real only when engineers turn them into machines. Voyager 2 launched first on August 20th, 1977. Voyager 1 launched a little later on September 5th, 1977. The names feel backward because Voyager 1 was placed on a faster path and would reach Jupiter and Saturn first. Voyager 2 took the slower road, but that slower road would eventually allow it to visit all 4 giant planets. Each spacecraft was about the size of a small car, though it did not look like one. It had a large dish antenna, long booms, cameras, instruments, and radioisotope thermoelectric generators that produced electricity from the heat of decaying plutonium. This mattered because sunlight gets weak very quickly as you travel outward. Solar panels that work near Earth become less useful near Jupiter and almost hopeless in the darkness beyond Saturn. Voyager needed its own long-lasting power source, and it carried something else. A golden record for science, but a message. Mounted on each spacecraft was a gold-plated copper phonograph record containing sounds and images from Earth. It held greetings in many languages, music from different cultures and eras, natural sounds like wind, thunder, birds, and whales, and images meant to show who we were, where we lived, and what kind of world had sent this machine into the dark. This record was not meant for us. It was meant for the possibility, however small, that sometime in the deep future, someone or something might find Voyager after its instruments had gone silent. It was a message placed on a spacecraft that would eventually outlive its makers, outlive the civilization that launched it, and perhaps outlive the languages spoken by the people who chose its contents. That makes Voyager different from most machines. Most machines are built to serve a purpose for a short time and then disappear. Voyager was built for science, but it also became a memory object, a moving artifact, a small piece of Earth sent into a galaxy that had never asked for it. But before Voyager became a messenger to the stars, it was a planetary explorer, and its first great destination was Jupiter. When Voyager 1 approached Jupiter in 1979, humanity saw the giant planet in a new way. Jupiter had been observed from Earth for centuries. Telescopes had revealed its bands, its moons, and its great red spot. But looking from Earth is like watching a storm through a keyhole from across an ocean. Voyager came close enough to turn Jupiter from an object into a place. The images showed swirling clouds, turbulent belts, and storms inside storms. The Great Red Spot was not just a red oval, it was a rotating system larger than Earth, with smaller storms moving around it like weather patterns inside a living atmosphere. The planet's colors were not decoration. They were the visible traces of chemistry, altitude, and motion. Jupiter did not look peaceful. It looked like a world made entirely of force. Voyager also discovered a thin ring around Jupiter, something that had not been known before. The ring was faint, not bright and dramatic like Saturn's, but it changed the way scientists understood the giant planet's environment. It showed that Jupiter was not only surrounded by moons, but also by dust and debris shaped by gravity and impacts. Then came the moons. Io was the shock. Before Voyager, scientists knew Io as one of Jupiter's large moons, but nobody expected it to be the most volcanically active world in the solar system. Voyager images revealed erupting plumes rising above its surface. This was not ancient geology frozen in place. It was a moon still violently changing. The explanation was tidal heating. Io is squeezed and stretched by Jupiter's gravity and by the gravitational influence of neighboring moons. That repeated flexing warms its interior, driving volcanoes that cover its surface with sulfur compounds and lava. A world that should have been cold because of its distance from the sun was being heated from within by gravity itself. That was one of Voyager's great lessons. The outer solar system was not dead. Europa, another moon of Jupiter, appeared smooth and icy, crossed by strange lines and cracks. It did not reveal its ocean directly, but Voyager helped begin the story that later missions would develop. The possibility that beneath Europa's frozen crust, there could be liquid water. The idea that an icy moon around Jupiter might hide an ocean became one of the most important possibilities in astrobiology. Ganymede and Callisto showed old, battered surfaces shaped by impacts and ancient history. Each moon had its own personality. The Jupiter system was not a simple planet with satellites. It was almost a miniature solar system, filled with radiation, volcanic activity, ice, magnetic fields, and gravitational drama. Voyager 1 then moved on to Saturn. Saturn was different. If Jupiter looked violent, Saturn looked unreal. Its rings were the main attraction. But Voyager revealed that they were not smooth bands. They were made of thousands of narrow ringlets, gaps, waves, and structures shaped by tiny moons and gravitational resonances. The rings behaved like a delicate machine made of ice and orbital mathematics. Saturn also brought one of the most important decisions in Voyager history. Voyager 1 was sent on a path that allowed it to closely observe Titan, Saturn's largest moon. Titan was fascinating because it had a thick atmosphere, something rare for a moon. Scientists wanted to know what was hidden beneath its orange haze. Voyager 1's flyby confirmed Titan's dense atmosphere, but the haze blocked the surface from view. That Titan encounter had a cost. The trajectory sent Voyager 1 upward, out of the plane of the planets. It would not continue to Uranus or Neptune. Its planetary tour ended at Saturn, and from there, it began a long climb out of the solar system. Voyager 2 continued the grand tour. It visited Uranus in 1986 and Neptune in 1989, becoming the only spacecraft ever to fly past those planets. It revealed Uranus as a strange tilted world with a magnetic field that did not behave as expected. It showed Neptune as a blue giant with powerful winds and dark storms, even though it receives so little sunlight. It discovered details about moons, rings, atmospheres, and magnetic fields that would have remained hidden for decades without it. By the end of the planetary encounters, the Voyager mission had changed the solar system. Not physically, of course, but in the human mind. Before Voyager, the outer solar system was distant and abstract. After Voyager, it was filled with landscapes, storms, rings, volcanoes, atmospheres, and mysteries. Then the cameras were no longer the most important instruments. The planets were behind the spacecraft. The next target was not a world, it was a boundary. That transition is easy to overlook. We remember the photographs because photographs are immediate. A moon covered in volcanoes is easy to understand. Saturn's rings are beautiful without explanation. Neptune's blue atmosphere can be placed on a poster. But the mission, after the planets became quieter, slower, and in many ways more profound, Voyager entered the long darkness between worlds. From Earth, it still communicated using radio signals. The spacecraft sent data back across billions of kilometers, and the Deep Space Network listened. These signals became weaker with distance. They traveled at the speed of light, but even light needed hours to cross the gap. A command sent from Earth would not reach Voyager immediately. A reply would not come quickly. The spacecraft was becoming remote in a way almost nothing human-made had ever been. And yet, it was still working. The instruments continued to measure charged particles, magnetic fields, plasma waves, and cosmic rays. These were not the kinds of discoveries that appear as colorful postcards. They were numbers, patterns, increases, decreases, changes in direction, and vibrations in plasma. They were clues from a region of space no spacecraft had ever sampled before. To understand why those clues mattered, we need to understand the shape of the sun's bubble. The heliosphere is often described as a bubble, but that word can be misleading. A soap bubble is thin and round. The heliosphere is vast, dynamic, and shaped by motion. The sun is not sitting still in the galaxy. It moves through the local interstellar medium, the thin gas and magnetic field between nearby stars. As it moves, its solar wind pushes outward, while interstellar material pushes back. This creates a boundary structure. Closer to the sun, the solar wind streams outward at supersonic speeds. Farther away, it eventually slows down. The place where the solar wind drops from supersonic to subsonic speed is called the termination shock. Beyond that is the heliosheath, a turbulent outer region where the solar wind has slowed and becomes compressed, heated, and disturbed. Farther still is the heliopause, the boundary where solar wind plasma gives way to interstellar plasma. Outside, that is interstellar space. But none of these layers are solid. They move, they breathe, they shift as the sun changes. Solar activity rises and falls in an approximately 11-year cycle. Coronal mass ejections and solar storms send disturbances outward. The pressure inside the heliosphere changes. The interstellar medium outside is not perfectly uniform, so the boundary is not a fixed wall. It is more like a moving shoreline between two invisible oceans. Voyager was heading toward that shoreline. The first major sign came when Voyager 1 reached the termination shock in 2004. This was the region where the solar wind, after racing outward for billions of kilometers, finally slowed down dramatically. The spacecraft had not left the heliosphere, but it had entered the heliosheath. It was now inside the outer shell of the sun's bubble, a place where the solar wind was no longer freely expanding. Voyager 2 crossed the termination shock later, in 2007, at a different distance and location. That difference mattered. It showed that the heliosphere was not perfectly symmetrical. The boundary was shaped by external pressure, solar activity, and the surrounding interstellar environment. This should already make the solar system feel stranger. The sun's domain is not a perfect sphere. It is a distorted cavity carved into the galaxy. The planets orbit inside it like passengers inside a moving ship, while the ship itself plows through a thin galactic sea. Voyager was not simply moving away from the sun. It was moving toward the hull of that ship, toward the place where the outside ocean begins. Inside the heliosheath, Voyager measured a strange environment. The solar wind had slowed. Charged particles behaved differently. Magnetic fields became more important. Cosmic rays, high-energy particles from outside the solar system, became part of the story. Cosmic rays are dangerous and revealing. They come from beyond the heliosphere, from energetic events in the galaxy, such as supernova remnants and other powerful astrophysical processes. The heliosphere acts like a partial shield against them. It does not block them completely, but it reduces their intensity inside the solar system. Earth has additional protection from its magnetic field and atmosphere. But far from Earth, near the edge of the heliosphere, Voyager could measure how this shielding changed. As Voyager 1 moved outward, scientists watched two kinds of particles. Particles from the sun and particles from the galaxy. If Voyager approached the heliopause, solar particles should drop because the spacecraft would be leaving the region dominated by the solar wind. galactic cosmic rays should rise because the spacecraft would be entering a region where outside particles were less blocked. For years, the data shifted gradually. Then, in 2012, something dramatic happened. Voyager 1 recorded a sharp decrease in particles from inside the heliosphere and a sharp increase in galactic cosmic rays. It looked like a crossing. But scientists were cautious. They had expected that the magnetic field direction might change significantly when Voyager crossed into interstellar space. Instead, the magnetic field direction remained surprisingly similar. This created confusion. Had Voyager crossed the heliopause? Had it entered a new layer still inside the heliosphere? Was the boundary more complicated than expected? This uncertainty is part of what makes the story honest. Science did not immediately announce a simple answer, because the data did not fit every expectation. The spacecraft had entered a region no human object had ever measured directly. Models were helpful, but the real boundary was allowed to be different from the boundary imagined in diagrams. For months, scientists analyzed the evidence. The particle data strongly suggested that Voyager 1 had left the heliosphere, but one crucial measurement was missing. Voyager 1's plasma instrument, which could have directly measured the solar wind plasma, had stopped working decades earlier. Without it, scientists needed another way to determine whether the spacecraft was surrounded by interstellar plasma rather than solar plasma. The answer came from waves, not sound waves traveling through air. There is no air out there. These were plasma waves, vibrations in ionized gas. When solar eruptions sent disturbances outward, those disturbances eventually reached the region around Voyager and made the surrounding plasma oscillate. Voyager's plasma wave instrument could detect those oscillations. From their frequency, scientists could estimate the density of the plasma. This was the key. Interstellar plasma is denser than the plasma expected inside the outer heliosphere. When Voyager detected plasma oscillations showing a higher density environment, the evidence became much stronger. The spacecraft was in interstellar space. Voyager 1 had crossed the heliopause on August 25, 2012. At that moment, it was about 122 astronomical units from the Sun, roughly 18 billion kilometers from the Sun. Depending on the exact date and geometry, the distance from Earth was also enormous, shifting as Earth moved in its orbit, and Voyager continued outward. But the important fact is this: Voyager had reached the boundary where the Sun's wind gave way to the matter between stars. It had not left the Sun's gravity behind. That would take far longer. It had not passed beyond every object connected to the solar system. The distant Oort cloud, if considered part of the solar system, extends much farther. Voyager will take thousands of years to pass through that region. But it had left the heliosphere. It had entered interstellar space. And what it found there was not empty, nothing. It found the galaxy pressing against us. That idea is easy to miss because space is so thin. The interstellar medium is far emptier than any vacuum we can easily create in ordinary life. A cubic centimeter of air at sea level contains an enormous number of molecules. A cubic centimeter of interstellar space may contain only a few particles, or less, depending on the region. It sounds like nothing, but over astronomical distances, even thin gas matters. Magnetic fields matter, radiation matters, pressure matters. The heliopause exists because the solar wind and the interstellar medium are in a kind of balance. The Sun pushes outward, the galaxy pushes inward. Voyager reached the place where those pressures meet. This means the solar system has weather on a scale that makes Earth weather look tiny. There are solar storms that race outward for months. There are changes in cosmic ray intensity. There are waves passing through plasma. There are magnetic structures draped around the heliopause. There are boundaries that shift over time. The edge of the solar system is not a quiet line. It is a living interaction between a star and the galaxy around it. And Voyager was the first thing we ever built. that could touch that interaction directly. But to appreciate how strange that is, we have to step back and think about what 18 billion kilometers really means. A kilometer is already a human-sized unit stretched a little beyond daily comfort. You can walk 1 kilometer. You can drive 10. A plane can cross thousands. But 18 billion kilometers is not a distance the human mind handles naturally. Light travels about 300,000 kilometers every second. At that speed, light can circle Earth several times in 1 second. Light from the moon reaches Earth in a little over 1 second. Light from the sun takes about 8 minutes to reach us. A radio signal from Voyager near the heliopause took more than 16 hours to reach Earth. That means when Voyager sent its data, Earth did not hear it as something happening now. We heard an echo from half a day earlier, and as Voyager travels farther, the delay grows. Communication becomes less like controlling a machine and more like exchanging messages with a ghost, moving steadily into the dark. The spacecraft cannot be steered in the ordinary sense anymore. Engineers can send commands, but they must wait for the signal to cross the void, then wait again for the spacecraft's response. Every conversation is stretched by distance. Every bit of data is precious, because the spacecraft's power is fading, its instruments are aging, and its signal is faint. The radio transmitter on Voyager is weak compared with anything we imagine as powerful broadcasting. By the time its signal reaches Earth, it is unimaginably faint. The Deep Space Network uses huge antennas to listen for it, separating it from background noise, catching the whisper of a machine launched in 1977. That alone should feel impossible. A spacecraft older than many of the people now working on it is still speaking from beyond the sun's bubble. But Voyager's journey to that boundary was not only a story of distance, it was a story of survival. Spacecraft do not last by accident. They are designed, tested, protected, and then left to face conditions no laboratory can perfectly recreate. Voyager had to survive launch vibrations, planetary radiation belts, cold, heat, vacuum, aging electronics, decreasing power, and decades of cosmic radiation. Its computers are primitive by modern standards. Its memory is tiny compared with even simple devices today, yet its simplicity became part of its strength. It was built in an era when hardware had to be reliable, because repair was impossible. There is something humbling about that. We often think of technology as getting better, because it becomes faster, smaller, and more complex. Voyager reminds us that endurance is another kind of intelligence. A machine does not need a modern screen, a fast processor, or a sleek design to become one of humanity's greatest explorers. It needs purpose, careful engineering, and enough resilience to keep functioning after everyone expected the mission to be over. The original planetary mission lasted years. The interstellar mission has lasted decades. And in that long extension, Voyager changed from a camera-bearing explorer into a boundary detector. It no longer shows us planets. It shows us where the sun ends as an environment. That is why the phrase, "what Voyager found," can be misleading if we imagine a single object. Voyager did not find a planet, a wall, or an alien structure. It found a transition. It found evidence that the space around the sun has an edge, not in gravity, but in plasma. It found that the galaxy is not just distant stars on the night sky. The galaxy has material around us right now, touching the outside of the heliosphere. It found that Earth lives inside a protective bubble, and that bubble is finite. This is one of the most quietly terrifying facts in space science. We are used to thinking of danger as something dramatic. Asteroids, black holes, supernovas, giant storms. But some dangers are not dramatic. They are environmental. They are the background conditions that make life possible or impossible. The heliosphere helps shield the inner solar system from some galactic cosmic rays. Earth adds its own protection with its magnetic field and atmosphere. Life on the surface exists inside layers of defense we rarely think about. Remove one layer, and the environment becomes harsher. Remove several, and space becomes lethal. Voyager went beyond one of those layers. It crossed out of the sun's main protective bubble and entered a region where galactic particles are more common. The spacecraft did not die instantly. It is not alive, and it was built to endure radiation. But the data it returned reminds us that the solar system is not isolated from the galaxy. We are not sealed away. We are surrounded by a larger environment that constantly presses against the sun's domain. And the sun is moving through it. This matters because the heliosphere may change depending on the local interstellar environment. If the sun moves into a denser region of interstellar gas in the distant future, the heliosphere could shrink. If external pressure changes, the boundary could move. The protective bubble around the planets is not a permanent glass sphere. It is a dynamic structure created by a star traveling through a galaxy. Voyager gave us the first direct measurement of that reality, but it also gave us something more emotional than data. It gave us perspective. In 1990, after Voyager 1 had finished its planetary mission, it turned its camera back toward the inner solar system and took a final family portrait. Among those images was Earth, seen from about 6 billion kilometers away. In that photograph, our planet appears as a tiny point of light, a pale blue dot suspended in a sunbeam. That image was not taken at 18 billion kilometers. It came earlier in the journey, but it belongs in this story because it shows what Voyager was leaving behind. Every ocean, every city, every forest, every war, every person who had ever looked up and wondered what space was. All of it fit inside one pixel. Then, the cameras were turned off to save power, and Voyager continued outward, no longer looking back. There is a strange mercy in that. The spacecraft did not need eyes anymore. Its work became deeper than images. It listened to particles. It measured fields. It felt the invisible. The most important part of its journey would not be photographed, because the edge of the heliosphere is not something a camera can capture in a simple frame. This is one reason the Voyager story feels almost like a myth, even though it is engineering and science. A small object leaves home. It visits giants. It receives speed from them. It turns back once and sees home as a speck. Then it goes blind by choice, saving its strength for the darkness ahead. Years later, it reaches a boundary no eye can see and tells its makers that the sun's kingdom has an edge. That sounds like a story written by people trying to make space poetic, but it really happened. The poetry came from the physics. Now, before we go deeper into what Voyager found near the heliopause, we need to understand why the sun creates a bubble in the first place. The sun's outer atmosphere, the corona, is extremely hot. It is so hot that some particles move fast enough to escape the sun's gravity. These particles stream outward as solar wind. Near Earth, the solar wind interacts with our magnetic field, compressing it on the day side and stretching it into a long magnetotail on the night side. When solar storms hit, they can trigger auroras, disturb satellites, affect radio communication, and induce currents in power systems. That is, space weather. But space weather does not stop near Earth. The solar wind keeps moving outward, past Mars, past the asteroid belt, past Jupiter, past Saturn, past Uranus, and past Neptune. As it expands, it becomes thinner. Its pressure drops. Eventually, it becomes too weak to push outward freely against the surrounding interstellar medium. At the termination shock, it slows. In the helios sheath, it becomes turbulent. At the heliopause, it is stopped by the interstellar environment. That is the simplified version. The real version is messier. Magnetic fields spiral outward from the rotating sun in a structure often called the Parker spiral. Solar activity changes over time. The heliosphere may have a nose and a tail, or a more complex shape than older comet-like models suggested. The local interstellar magnetic field affects the boundary. Energetic neutral atoms, measured by other missions such as IBEX, have revealed global features that Voyager alone could not map. Voyager gave us local truth. Other missions help fill in the wider picture. This is important because Voyager crossed only along specific paths. Voyager 1 and Voyager 2 left the heliosphere in different directions at different times and at slightly different distances. They are like two needles passing through a vast invisible surface. From those two crossings, scientists learn a tremendous amount, but the entire boundary remains larger and more complex than any two spacecraft can describe fully. Imagine trying to understand Earth's oceans by sailing two straight lines across them. You would learn real things. You would measure waves, temperatures, winds, currents, and depths along those paths. But the ocean would still be bigger than your tracks. The heliosphere is like that. Voyager touched it directly, but it did not map every part of it. That is why each measurement matters so much. We may not get many chances like this. No other spacecraft has traveled as far and continued returning this kind of data from beyond the heliopause. The New Horizons spacecraft, which flew past Pluto in 2015, is also traveling outward, but it is on a different mission and with different capabilities. The Voyager probes remain unique because they are still operating in interstellar space, sending back measurements from a region that was once entirely theoretical. When Voyager 1 crossed the heliopause, the signal was not a dramatic scream. It was a pattern in the data, a decrease in particles from the sun, an increase in galactic cosmic rays. Later, plasma wave measurements showing the density of interstellar plasma. This is how space often reveals itself, not as a cinematic event, but as numbers changing in a way that only makes sense if the spacecraft has entered a new environment. That may seem less exciting at first, but it is actually more powerful. A photograph can show you what something looks like. A measurement can tell you what something is. Voyager's discovery was not about appearance. It was about identity. The spacecraft was no longer inside the same plasma environment as Earth. It had crossed into the material between stars. Now, think about that phrase carefully. Interstellar space. It sounds like pure emptiness. It sounds like the black gap between suns, the place where nothing belongs. But interstellar space is not empty in the absolute sense. It contains gas, dust, magnetic fields, cosmic rays, and radiation. It is thin beyond ordinary imagination, but it is not nothing. The sun moves through a region called the local interstellar cloud, a warm, partially ionized cloud within a larger low-density region known as the local bubble. These names can make the galaxy sound soft, almost gentle. Cloud, bubble, local. But they describe enormous structures shaped by ancient stars, stellar winds, and supernova explosions. Our solar system is not floating in a blank void. It is moving through galactic weather created by the lives and deaths of stars. The atoms outside the heliosphere may have histories older than the sun. Some were forged in earlier generations of stars. Some were pushed around by explosions long before Earth formed. Some are part of a diffuse environment that our sun happens to be traveling through right now. Voyager is sampling that environment directly. This is why the mission is not only about the solar system. It is about our place in the Milky Way. For most of human history, the galaxy was something seen from inside, as a pale band of light across dark skies. Later, telescopes revealed that it was a vast system of stars. Later still, science showed that the sun is only one star among hundreds of billions. But all of that knowledge still came mostly from light, from observations across distance. Voyager gives us something different. It gives us touch. Not human touch, but instrumental touch. A magnetometer sensing the local field. A cosmic ray detector counting energetic particles. A plasma wave instrument hearing vibrations in ionized gas. It is the difference between looking at smoke across a room and placing a sensor inside the smoke itself. Voyager is inside the boundary region of our galactic environment. That fact is almost easy to say. It is much harder to absorb because the spacecraft is small. Its high-gain antenna is only a few meters across. Its computers are ancient. Its power is fading year by year. Its data rate is tiny. It is not a giant starship. It is not a science fiction vessel with engines burning bright. It is a quiet machine coasting through darkness, using momentum gained decades ago, speaking in weak radio signals, carrying a golden record no one may ever play. And yet it reached the edge of the sun's bubble. There is a kind of terror in that distance, but not the loud kind. It is the terror of realizing that the solar system is both enormous and fragile. Enormous, because it takes decades for even a fast spacecraft to reach the heliopause. Fragile, because the sun's influence eventually fades into the background of the galaxy. The sun feels absolute from Earth. It dominates our sky. It warms the oceans. It drives weather. It powers photosynthesis. It defines day and night, seasons, and the rhythm of life. But from Voyager's distance, the sun is only a bright star, still important, still gravitationally dominant, still the source of the spacecraft's origin, but visually reduced. This is one of the hidden emotional turns in the Voyager story. At first, Voyager makes planets feel close. It brings Jupiter, Saturn, Uranus, and Neptune into view. It gives humanity images and details. It shrinks the unknown by visiting it. Then, after the planets, Voyager does the opposite. It makes everything feel larger again. It shows that even after you pass the giant planets, even after the sun is no longer warm, even after Earth is invisible without instruments, you are still not truly at the end. You are only approaching the outer boundary of one kind of solar influence. Beyond that lie the Oort cloud, nearby stars, the rest of the galaxy, and distances so large that Voyager will not reach another star for tens of thousands of years. This is why 18 billion kilometers is both unbelievably far and almost nothing. For a human life, it is enormous. For the galaxy, it is a doorstep. Voyager crossing the heliopause is like a person leaving the porch of a house and stepping into a continent. It is meaningful. It is historic. It changes the environment around them. But it does not mean they have crossed the whole land. The spacecraft has entered interstellar space, but it has barely begun interstellar travel. That distinction matters for the title of this video. What Voyager found 18 billion kilometers from Earth was not the end of space. It was the end of the sun's main protective wind. It was the beginning of direct contact with the galaxy. It was the discovery that the boundary around our home star is real, measurable, and stranger than a simple line. Now, to understand why that discovery took so long to confirm, imagine being a scientist waiting for data from a spacecraft that is farther away than anything humans have ever controlled. You cannot go there. You cannot fix an instrument. You cannot ask for a quick second look. You receive streams of numbers from a machine at the edge of the sun's domain, and those numbers arrive after traveling for hours as radio waves. Some instruments are still active. Some are dead. Some data are clear. Some are ambiguous. The environment itself is unfamiliar. Every expectation comes from models, and every model is about to be tested against reality. This is not like identifying a continent from a ship's deck. It is more like listening to waves under a locked door and trying to decide what kind of ocean is on the other side. That is why the 2012 crossing was not immediately obvious to everyone. The cosmic ray data changed sharply. The lower energy particles from the heliosphere dropped. The galactic particles rose. Those signs pointed strongly toward a boundary crossing. But the magnetic field did not rotate in the simple way many scientists expected. In some stories, that detail would be skipped because it complicates the moment. But the complication is the point. The heliopause was not exactly the boundary in the textbook picture. It was a real physical transition shaped by plasma behavior, magnetic fields, and the geometry of the local interstellar environment. Voyager did not merely confirm old expectations, it forced scientists to refine them. This is one of the greatest values of exploration. You do not send a spacecraft across billions of kilometers only to prove that your drawing was perfect. You send it because reality has details the drawing cannot contain. Voyager carried that truth all the way to the heliopause. The second Voyager crossing made the story stronger. Voyager 2 reached interstellar space in 2018. Unlike Voyager 1, it still had a working plasma science instrument, so it could measure the solar wind plasma more directly, before and during the transition. Its crossing happened at a slightly different distance, in a different direction, and under different solar conditions. This mattered because it gave scientists a second point of contact with the heliopause. A single crossing can be historic. Two crossings begin to reveal shape. Voyager 2 confirmed that the heliopause is not a fantasy boundary. It is a real transition between the sun's plasma and interstellar plasma. But it also showed that the boundary can vary. The solar system is not wrapped in a perfect shell. The sun's bubble is shaped by motion, magnetic fields, particle pressure, and time. This is why the word edge needs care. There are many edges. There is the orbit of Neptune, the outermost major planet. There is the Kuiper Belt, where icy bodies orbit beyond Neptune. There is the heliopause, where the solar wind gives way to interstellar plasma. There is the distant Oort cloud, a vast population of icy objects that may extend far beyond the heliopause. There is the limit where the sun's gravity becomes weaker than the gravity of passing stars and the galaxy. So when someone asks where the solar system ends, the honest answer is, it depends what you mean by solar system. If you mean the planets, the edge is near Neptune and the Kuiper Belt. If you mean the sun's wind, the edge is the heliopause. If you mean the sun's distant comet cloud, the edge is far beyond Voyager's current position. Voyager's great discovery belongs to the second meaning. It found the edge of the solar wind's kingdom. And that is the edge that matters for understanding the sun as a protective environment. This is also why the number 18 billion kilometers is so powerful. It is not the final edge of everything connected to the sun, but it is far enough for the sun's wind to lose its dominance. It is far enough that Voyager moved from one kind of space into another. It is far enough that the spacecraft could tell us the galaxy begins much closer in a plasma sense than the Oort cloud suggests. The solar system, in other words, has layers. The planets are one layer. The icy outskirts are another. The heliosphere is another. Gravity reaches farther than plasma. Comets travel farther than solar wind. Influence is not one thing. This makes the true architecture of our home system far more interesting than the simple diagram. Earth is not merely the third planet from the sun. It is inside a magnetosphere, inside a solar wind bubble, inside a local interstellar cloud, inside a galaxy, inside a universe that has been expanding for billions of years. Every layer matters. Every layer changes the conditions around us. Voyager crossed one of those layers and showed us the next one directly. Now we can ask a deeper question. What does it actually mean to be outside the heliosphere? It does not mean the sun disappears. The sun's gravity still holds Voyager on a trajectory connected to the solar system. The sun's light still reaches the spacecraft, though it is faint. Radio signals from Earth still travel to it and back. Voyager is not free from the sun in every sense, but the particles around it are different. The cosmic ray environment is different. The plasma density is different. The magnetic field belongs more to the interstellar environment than to the solar wind. This is why Voyager's crossing was not a visual event. If a human could somehow stand next to the spacecraft, protected by impossible technology, they would not see a glowing border. They would see darkness. The sun would appear as a bright star. Other stars would look much like they do from Earth, though without our atmosphere. The Milky Way would stretch across the sky. There would be no signpost, no curtain, no visible membrane. The difference would be invisible, but deadly real. It would be in the particles passing through your body. It would be in the plasma around your instruments. It would be in the balance of magnetic forces. It would be in the fact that the wind from the sun no longer owns the space you occupy. This is one of the central ideas of the Voyager story. Some of the most important borders in the universe cannot be seen. Earth's atmosphere has layers you cannot easily see from the ground. Earth's magnetic field is invisible, yet it guides charged particles and helps protect the planet. The heliopause is the same kind of boundary on a much larger scale. It is not made for human eyes. It is made by physics. Voyager found it because Voyager was built to measure what eyes cannot. This is why the mission becomes more mysterious after the photographs end. During the planetary flybys, the discoveries were visually spectacular. A volcano on Io, braided structure in Saturn's rings, clouds on Neptune, a moon with an atmosphere. These images made headlines because they could be seen and understood quickly. The interstellar mission is quieter. There are no new pictures of the heliopause. There are no dramatic landscapes. There is only the deep behavior of space itself, and in a way, that is more unsettling. A landscape can feel alien, but at least it is a place. You can imagine standing there. You can imagine mountains, ice, dust, or clouds. The heliopause is not like that. It is a condition. It is an invisible agreement between the sun and the galaxy. It is the point where one environment yields to another. Voyager found that agreement written in particles. And the first half of this script is really the story of how it got there. It began as a mission designed around a planetary alignment. It became the first tour of the outer giants. It revealed that the outer solar system was active, complicated, and surprising. It turned back once and showed Earth as a pale dot. Then it flew onward for more than 20 additional years, measuring a boundary nobody had touched before. The next half of the story belongs to what happened after the crossing, because entering interstellar space did not end the mission. It opened a new one. Out there, Voyager began listening to the faint vibrations of interstellar plasma. It measured cosmic rays in a region beyond the sun's main shielding. It continued to test how the magnetic field behaves outside the heliosphere. It became a probe not of planets, but of the local galactic environment. And the more scientists studied those measurements, the more the edge of the solar system stopped looking like a clean border. It began to look like a complex frontier, a region shaped by storms from the sun, pressure from the galaxy, and waves moving through plasma. A place where the space between stars is not empty. A place where the sun's protection ends. But the story of the solar system continues. Before we continue into those discoveries, there is one more thing to understand about Voyager's position in time. The spacecraft is not just far away in space. It is also far away from the era that built it. When Voyager launched, there were no smartphones. The internet did not exist in daily life. Personal computers were primitive. Many of today's scientists grew up in a world that Voyager had already left. The spacecraft is a functioning piece of the 1970s, still operating in the 21st century, beyond the planets, beyond the heliopause, beyond the environment it was originally expected to explore. That makes every signal feel like a message from two distances at once, a distance in kilometers, and a distance in history. The engineers who built it designed for possibilities they knew they might never personally see. Some of the people who worked on the mission are gone now. Others spent entire careers following the same spacecraft farther and farther outward. New generations inherited the responsibility of listening to it, solving its problems, conserving its power, and deciding which instruments could remain active as the energy supply slowly declined. This is the human side of deep space exploration. A spacecraft may travel alone, but a mission does not. It is carried by teams across decades. Every command sent to Voyager is part of a chain of work that began before many viewers of this video were born. Every bit of data received today is the result of decisions made in another technological age. The machine is far away, but the mission remains connected to Earth by attention, patience, and radio waves. That connection will not last forever. The spacecraft's power continues to fall as its plutonium heat source decays. Instruments have been turned off over time to preserve the most valuable science for as long as possible. Eventually, Voyager will no longer have enough power to communicate. One day, Earth will listen, and the signal will not come. But that day has not fully arrived yet. And while Voyager can still speak, it is telling us about the place where the sun's bubble meets the galaxy. That is why this mission matters now. Not only because of what it did at Jupiter, not only because of what it saw at Saturn, not only because of the golden record or the pale blue dot, but because it is still teaching us what kind of space surrounds our home. When we look up at the night sky, the stars appear separate. Each one seems like a distant lamp in darkness. But Voyager reminds us that the space between those lamps is a physical environment. Thin, yes. Dark, yes. Nearly empty by human standards, yes, but filled with fields, particles, histories, and pressures. The galaxy is not just something we see, it is something the sun is inside. And Voyager is the first human-built object to cross from the sun's main plasma bubble into that wider environment. So as we move into the second half of this journey, keep this image in mind: a small spacecraft moving silently through blackness, far beyond the planets. Behind it, the sun and everything we know. Around it, plasma from between the stars. Ahead of it, a future so long that human history becomes almost invisible. And inside its memory, a record of Earth, waiting for a listener that may never exist. Voyager did not find a wall at 18 billion kilometers. It found something more important. It found that our solar system has a boundary made of invisible forces, and that beyond it, the galaxy is not empty at all. The next question is what that galaxy-side darkness actually sounds like to a machine still listening in the night. But before we cross fully into that second half, pause on the meaning of the journey itself. Voyager did not discover the edge because it was looking for a dramatic final destination. It discovered the edge because it kept measuring after the famous moments were over. The greatest part of the mission came not from one photograph, one planet, or one headline, but from the patience to keep listening as the spacecraft moved into a place where no camera could tell the whole truth. That is the quiet power of Voyager. It proves that the universe does not always reveal its deepest borders through light. Sometimes it reveals them through a change in particles, a vibration in plasma, a delayed radio signal, and a machine small enough to disappear against the stars. And in that darkness, the next thing Voyager found was not an object. It was a change in the environment that may sound less exciting than a new planet, a hidden moon, or some strange structure waiting beyond Neptune. But for the edge of the solar system, it was exactly the kind of discovery scientists had been waiting for, because the border around the sun is not drawn by rock. It is not marked by a cliff. It is not a ring of ice where everything suddenly stops. It is a boundary made from pressure, particles, magnetic fields, and motion. To understand what Voyager found, we have to let go of the idea that the solar system ends the way a country ends on a map. There is no line painted across space. There is no gate. There is no dramatic wall where sunlight cuts off. Even far beyond Pluto, the sun is still visible. Even far beyond the planets, Gravity from the sun still reaches outward, but the solar wind, the stream of charged particles blowing from the sun, does not travel forever with the same strength. It expands, it thins, it weakens, and eventually it runs into the material that fills the space between stars. That meeting place is what Voyager reached. Inside the heliosphere, the spacecraft was still traveling through a region shaped mainly by the sun. Outside the heliosphere, it entered a region shaped mainly by the galaxy. The change was not visible to a camera, but it was written in the particles striking the spacecraft and in the faint electric vibrations of plasma around it. This is why Voyager's greatest discovery at 18 billion kilometers was so strange. It did not send back a photograph of the edge. It sent back evidence that the edge was real. Cosmic rays increased, solar particles dropped, plasma density changed, magnetic measurements behaved in ways scientists did not fully expect. And suddenly, a spacecraft built in the 1970s was no longer only a machine that had visited planets. It had become a probe of the local interstellar medium. That phrase sounds calm, almost technical. The local interstellar medium. But what it means is far more dramatic. It is the material between the stars near our solar system, not empty space, not pure nothing. A thin, dark, almost invisible mixture of ions, electrons, neutral atoms, dust grains, magnetic fields, and radiation left behind by generations of stars that lived and died before the sun was born. When Voyager crossed the heliopause, it moved from the sun's protective bubble into that galactic environment. For the first time, something made by humans was not just looking at interstellar space from a distance. It was inside it. And this matters because from Earth, we usually imagine interstellar space as a black gap, a silent distance between the stars. But the Voyagers showed that the gap has structure, it has pressure, it has density. It has storms that begin at the sun and travel outward until they shake the plasma beyond the heliopause. It has cosmic rays coming from outside the solar system, particles that have been accelerated by violent events across the galaxy. It has a magnetic field that does not behave as neatly as expected. The emptiness between stars is not empty. It is just too thin for our senses to understand. If you could somehow stand beside Voyager, protected from the cold, the radiation, and the vacuum, you would not see a bright border behind you. The sun would look like an unusually bright star. Earth would be completely invisible. The giant planets would be lost in the black. Around you, there would be no glowing fog and no shining surface. The edge of the solar system would not announce itself visually, but the instruments would know. They would feel the galaxy pressing back. One of the clearest signs came from cosmic rays. These are high-energy particles that come from outside the heliosphere. Many are thought to be accelerated by supernova remnants and other violent astrophysical processes. Inside the sun's bubble, the heliosphere helps shield the planets from a large portion of them. It does not block everything, but it reduces the amount that reaches the inner solar system. That protection is easy to ignore from Earth because we live beneath another layer of defense. We have a magnetic field, we have an atmosphere, we have distance from deep space. But Voyager was far beyond that comfort. It carried particle instruments that could count what was hitting it. As it neared and crossed the heliopause, the number of particles from inside the heliosphere fell sharply, while the number of galactic cosmic rays rose. That was one of the signatures scientists were waiting for. It was as if Voyager had moved from one ocean current into another. The water did not vanish, but the direction, speed, and character of the flow changed. The solar system, at that distance, became less like a set of planets and more like a bubble traveling through a galactic sea. And that idea is unsettling, not because it makes the sun weak, but because it reveals that the sun itself is moving through an environment larger than its own influence. Our star is not a fixed center of reality. It is a moving object inside the Milky Way, carrying its planets, moons, comets, dust, and all of us through interstellar material. The heliosphere is the sun's moving shelter. Voyager found the outside of that shelter. But once it crossed, scientists faced a problem. Voyager 1 had become the first spacecraft to enter interstellar space. Yet one of the instruments that would have measured the plasma directly had stopped working decades earlier. That failure could have made the crossing harder to confirm. A camera could not help. The stars looked essentially the same. The spacecraft did not bump into a barrier, so the team needed another way to prove that Voyager was surrounded by denser interstellar plasma. The answer came through plasma waves. This is one of the most haunting parts of the mission. Voyager did not hear sound in the normal human sense. Space is far too empty for ordinary sound waves to travel the way they move through air, but plasma can oscillate. Charged particles can vibrate collectively. Instruments can detect those electrical vibrations. Scientists can then convert those measurements into audio frequencies, creating eerie tones that represent the plasma environment around the spacecraft. So when people say, Voyager heard interstellar space, they are using a poetic shortcut. It did not hear with ears, it measured waves in a thin charged medium. Still, the result is powerful, because those waves revealed the density of the plasma around Voyager. The frequency of plasma oscillations depends on the number of electrons nearby. Higher density produces a different signal than lower density. By listening to these faint vibrations, scientists could infer that Voyager 1 was moving through a denser region than the hot, sparse plasma inside the heliosphere. That was the clue that confirmed the spacecraft had truly crossed into interstellar space. Imagine the scene: a machine launched before smartphones, before the modern internet, before most of today's viewers were born, is drifting more than 18 billion kilometers away. It cannot turn around and take a useful picture of Earth. It cannot scoop up material in a dramatic sample container. It cannot burn an engine and come home. Yet, by listening to tiny vibrations in plasma, it tells us where the sun's bubble ends. That is not science fiction. That is the real mission. And Voyager 2 made the story even stronger, because it crossed the heliopause later with a working plasma instrument. Unlike Voyager 1, it could directly measure the plasma environment as it entered interstellar space. Its data confirmed that the plasma outside the heliosphere was significantly denser and colder than the plasma inside. That result matched the broad expectation. But the details were not simple. The outer boundary was not a clean shell. The plasma seemed compressed near the edge. Particles appeared to leak through in places. The region just beyond the heliopause was not completely undisturbed interstellar space, but a transitional zone still affected by the sun's long reach. This is important because it changes the way we imagine the edge. The heliopause is not a perfect glass dome around the solar system. It breathes, shifts, and reacts to the sun's activity. The solar cycle rises and falls roughly every 11 years. Strong solar events send waves outward through the heliosphere. Over months and years, those waves can reach the distant boundary and disturb the plasma beyond it. In other words, even after Voyager crossed the edge, it was not entirely free of the sun. The sun could still touch the space around it through pressure waves. That may be the most surprising part. The edge is real, but it is not final. It separates two regions, yet those regions still interact. The sun pushes outward, the galaxy pushes inward. The heliopause forms where those pressures balance. When the sun becomes more active, the bubble can swell. When solar activity drops, the bubble can contract. Voyager did not pass through a fixed wall. It passed through a moving, living border. This is why the phrase edge of the solar system is both useful and misleading. It gives us a picture, but the real thing is stranger. At that distance, The solar system is not a neat object floating in space. It is a storm-shaped cavity carved into interstellar material by the sun's wind. Its boundary is invisible, flexible, and porous. It has a nose, flanks, and a tail-like structure shaped by the sun's motion through the galaxy. It is less like the edge of a planet and more like the boundary around a flame in moving air. Voyager's instruments cross that boundary one measurement at a time, not with drama, with numbers, and the numbers were enough to change our map of home. Before Voyager, the outer solar system was mostly theoretical beyond the planets. Scientists could model the heliosphere. They could estimate where the solar wind should slow down. They could imagine the termination shock, the heliosheath, and the heliopause. But a model is not the same as touching the boundary with a spacecraft. Voyager turned a prediction into a place. It made the edge measurable. First came the termination shock, where the solar wind slowed from supersonic speed as it began to feel the pressure of interstellar material. Then came the heliosheath, the turbulent outer layer where the sun's wind was still present, but altered and slowed. Finally came the heliopause, where solar wind plasma no longer dominated, and the spacecraft entered interstellar space. Each region told a different story. The termination shock said the sun's outward flow was losing its power. The heliosheath said the boundary was turbulent, compressed, and complicated. The heliopause said the galaxy had finally become stronger than the solar wind. This is what Voyager found at that immense distance. Not a single discovery, but an entire sequence of invisible environments that no human had ever directly measured before. And the deeper you think about it, the more personal it becomes. Because the heliosphere is not just a physics feature. It is part of why the inner solar system is the way it is. It helps reduce the incoming flux of galactic cosmic rays. It creates a protective bubble around the planets. It connects Earth to the sun, not only by light and gravity, but by a vast magnetic and particle environment reaching far beyond the known planets. When Voyager crossed the heliopause, it was like watching a small boat leave the harbor of the sun. Behind it was the region that shaped our world. Ahead of it was the galaxy without that shelter. That thought can feel strangely lonely. Voyager is often described as humanity's most distant spacecraft, but distance alone is not what makes it haunting. A number can grow so large that it becomes meaningless. 18 billion kilometers, 20 billion, 25 billion. At some point, the mind stops feeling the difference. What matters is what that distance represents. It represents a delay so long that communication becomes a slow conversation with the past. It represents sunlight weakened into a star-like point. It represents a spacecraft so far away that every command must be sent with patience, and every answer returns from a place no living human can reach. And it represents a discovery that cannot be photographed in the normal sense. At the edge, the camera was no longer the hero. The plasma instruments were, the magnetometer was, the cosmic ray detector was. The radio signal itself became part of the story. This is why Voyager is different from most space missions. Many missions are remembered through images. Hubble's nebulae, Webb's deep fields, Cassini's Saturn, New Horizons' Pluto. But Voyager's interstellar mission is remembered through invisible changes. A graph rising, another dropping, a frequency shifting, a magnetic field refusing to turn the way some scientists expected. The mission became quieter as it became more profound. The farther Voyager traveled, the less spectacular its view became to the eye, but the more unique its measurements became to science. Near Jupiter, it saw storms and moons. Near Saturn, it saw rings and icy worlds. Near the heliopause, it saw almost nothing visually, yet found a boundary that defines the sun's place in the galaxy. That is the kind of discovery that changes how we imagine home. Not by showing us a new world, but by showing us that our entire system is inside a bubble. The next question is what happens outside that bubble? The short answer is that Voyager entered interstellar space. The longer answer is more careful. It entered the very local interstellar medium, the nearby material just beyond the heliopause. This is still a region influenced by the Sun's recent history, because solar disturbances can cross the boundary and shake the plasma outside. Voyager is not suddenly floating in some perfectly calm, untouched galactic wilderness. It is in a transition between solar influence and the wider environment of the Milky Way. That difference matters. Interstellar space is not uniform. The Sun is traveling through a small region sometimes called the local interstellar cloud, a thin patch of partially ionized gas within a larger low-density region around the Sun. Different parts of the galaxy have different densities, temperatures, and magnetic conditions. If the solar system moved into a denser cloud, the heliosphere might shrink. If it moved through a thinner region, the bubble could expand. That means the size of the Sun's protective region is not permanent. It depends partly on where the Sun is in the galaxy. It depends on what the galaxy around us is doing. This makes the solar system feel less isolated and more exposed. We are not sitting in a static cosmic room. We are traveling through changing galactic weather. Most of the time, those changes are extremely slow by human standards, but they are real. The Sun's bubble is shaped by its journey, and Voyager is our first direct messenger into the material pressing against it. What did that messenger find? It found that cosmic rays become more intense outside the heliosphere. It found that the plasma density rises beyond the boundary. It found that the heliopause has layers, leaks, and disturbances. It found that the magnetic field just outside the bubble appears surprisingly aligned with the magnetic field inside, a result that challenged simple expectations. And it found that the Sun's influence does not end with a clean cut. It fades, transforms, and interacts. The magnetic field result deserves its own quiet moment, because it was one of the more puzzling discoveries. Scientists expected the magnetic field outside the heliosphere to be different from the field inside. Voyager 1 did see changes in particles that strongly suggested a crossing, but the magnetic field direction did not shift dramatically in the way many people anticipated. Later, Voyager 2 helped confirm that the magnetic field just outside the heliopause was roughly parallel to the field inside. This does not mean the spacecraft failed to cross. The particle and plasma data showed that it did. It means the boundary is shaped by magnetic connection in a more complex way than a simple classroom diagram might suggest. The heliosphere does not sit in the galaxy like a smooth bubble with completely separate magnetic fields on either side. The fields can drape, align, compress, and interact around the boundary. Again, the real edge is messier than the imagined edge. That messiness is valuable. Every surprise tells scientists where the model was too simple. The heliopause is not just a destination. It is a laboratory. It is a place where solar physics and galactic physics meet, and Voyager is the only spacecraft that has ever measured it directly from the outside. Think about how rare that is. We have sent orbiters around Mars. We have landed on Venus, Mars, Titan, asteroids, and comets. We have placed telescopes in space and watched galaxies near the edge of the observable universe. But only 2 spacecraft have crossed into interstellar space. Only 2 have sampled the boundary where the Sun's environment gives way to the galaxy. Both were built for a mission that was originally expected to last only a few years. That is why Voyager feels almost mythical, not because it escaped physics, but because it outlived expectations so dramatically that its secondary mission became historic. It was supposed to visit planets. Instead, it gave us the first direct measurements of the edge of the Sun's domain. And there is another terrifying detail hidden in this success. Voyager is moving incredibly fast by human standards, yet painfully slowly by interstellar standards. It crossed the heliopause after decades of travel. It is racing away from the sun at many kilometers per second. No human-made object on a normal escape path has gone farther. And still, compared with the distance to even the nearest stars, it is almost motionless. This is where the title becomes heavier. What Voyager found 18 billion kilometers from Earth is not only that the solar system has an edge, it found that the edge is close compared with the galaxy. That may sound strange. 18 billion kilometers feels impossible. It is far beyond anything a person can experience. It is so distant that a radio signal takes many hours to cross it. Yet, in interstellar terms, it is only the first step from the front door. The nearest stars are tens of trillions of kilometers away. The distance to Alpha Centauri is roughly 4 light years. Voyager has not traveled even 1 light day from Earth. This contrast is the quiet terror of the mission. The spacecraft reached the edge of the sun's bubble, and the galaxy barely began. It left the planets behind, but it did not arrive anywhere new in the ordinary sense. It moved beyond the heliopause, and then there was still almost everything ahead. That is what makes interstellar space feel different from the way science fiction often shows it. In fiction, leaving a solar system often means entering a highway between stars. In reality, it means entering a darkness so large that a spacecraft can travel for thousands of years and still pass near nothing. Stars are bright on the sky because they are powerful, not because they are close together. Between them, distance dominates. Voyager's future proves it. Long after it stops transmitting, it will continue moving. It does not need engines to keep going. In the vacuum of space, with no meaningful air resistance, it will coast along its trajectory around the center of the Milky Way. In tens of thousands of years, Voyager 1 will pass nearer to another star than it will be to the Sun at that time. But even that encounter will not be close in the way we normally mean. It will still be measured in light years. A spacecraft can spend 40,000 years traveling and still not enter another solar system. That single fact says more about the galaxy than almost any diagram. The Milky Way contains hundreds of billions of stars, yet space between them is so enormous that a tiny probe can wander for geological timescales without meeting one. Voyager is not heading toward a busy cosmic neighborhood. It is heading into a silence with rare islands of light. And yet, before it goes silent, it continues to send back data. That part of the story is easy to overlook because the planetary encounters were visually spectacular. But the interstellar mission is an engineering miracle. The spacecraft is powered by radioisotope thermoelectric generators, which produce electricity from the heat of decaying plutonium-238. That power has been declining for decades. Every year, the available energy falls. Engineers have had to turn off heaters, instruments, and systems to keep the spacecraft alive. A mission like this becomes a slow negotiation with death. Turn off this instrument to save another. Lower this power load to keep communications alive. Adjust this ancient system using commands sent across billions of kilometers. Wait almost a full day to learn whether the spacecraft obeyed. By the mid-2020s, Voyager 1 was more than 25 billion kilometers from Earth, and NASA was still fighting to keep it operating. Some instruments had to be shut down to preserve power. Engineers discussed and tested new energy-saving approaches to extend the life of the mission. The spacecraft that once returned images of Jupiter's clouds now survives through careful decisions measured in fractions of a watt. That is a different kind of drama. Not explosions, not landing legs, not a countdown. A team on Earth sends commands into darkness, knowing the answer will not come back until the spacecraft has already moved millions of kilometers farther away. The delay changes the emotional shape of the mission. With a rover on Mars, communication is delayed by minutes, With Voyager, the delay is measured in almost a day each way. If something goes wrong, engineers cannot simply react in the moment. They send a carefully prepared command, wait for it to cross interstellar distance, then wait again for the response. A problem becomes a 2-day conversation. The spacecraft is so far away that even troubleshooting feels like archaeology. Engineers are not just operating a machine, they are talking to a machine from another era. Its computers are primitive compared with modern devices. Its memory is tiny. Its hardware was built for a different technological world. Yet because the design was robust and the team has been patient, it still answers. There is something deeply human about that. Voyager is not powerful by modern standards. It is persistent. It survives by being understood. And every bit of data it returns is valuable because no other spacecraft is in the same place. When Voyager measures plasma waves or magnetic fields beyond the heliopause, there's no backup fleet surrounding it. There are no neighboring probes taking the same measurements from different directions. For decades, scientists had one direct crossing, then two points on an enormous boundary, two needles touching the skin of a bubble larger than the planetary system. That limitation is part of the mystery. The heliosphere is not fully mapped by Voyager. It is sampled. We know what the edge looked like where Voyager 1 crossed, and what it looked like where Voyager 2 crossed. Those crossings happened at different times, different latitudes, different positions, and under different phases of solar activity. From those two paths, scientists have to infer the shape and behavior of an enormous dynamic boundary. It is like trying to understand an ocean coastline by walking through two foggy points on it. The data are priceless, but the whole shape remains uncertain. That uncertainty is why future interstellar probe concepts matter. Scientists would like to send a new spacecraft, built specifically to explore the outer heliosphere and beyond. Such a mission could travel faster, carry modern instruments, and measure the boundary with far greater detail. It could answer questions Voyager could only begin to ask. How large is the heliosphere in different directions? How does the solar cycle reshape it over time? How exactly do galactic cosmic rays enter? What is the nature of the magnetic field beyond the heliopause? How does the sun's bubble compare with the astrospheres around other stars? Voyager gave us the first crossing. It did not give us the final map. That distinction is important for the video you are watching. The title asks what Voyager found, but the most honest answer is not a single thing. Voyager found a new region, a new boundary, and a new set of questions. It found that the solar system's edge is not empty. It found that interstellar space has weather of its own. It found that the sun protects us more than we usually feel. It found that the galaxy begins not with a wall, but with a shift in invisible conditions. And it found that even the first human-made object in interstellar space is still unimaginably far from the next star. This is the kind of discovery that grows more unsettling the longer you sit with it. At first, it sounds triumphant. We reached interstellar space. Then the scale catches up. We reached interstellar space, and there was still almost nothing around us. The boundary was not the entrance to a crowded cosmic city. It was the edge of a bubble opening into a desert, measured in light years. That desert is not literally empty, but it is empty in the way human life understands emptiness. There are atoms there, but so few that the best vacuum chambers on Earth still feel crowded by comparison. There are magnetic fields, but no wind on your face. There is radiation, but no warmth you could use. There are stars in every direction, but none close enough to change the loneliness of the spacecraft. This is why Voyager is such a strong symbol. It is not only far away, it is alone in a way nothing on Earth can be alone. A ship in the ocean is still surrounded by water, weather, sound, horizon, and the possibility of rescue. Voyager is surrounded by a thin galactic medium and an expanding delay in communication. It cannot be repaired by astronauts. It cannot be refueled. It cannot be redirected to a meaningful destination. It is a one-way message written in metal, circuitry, and radioactive warmth. And eventually, that warmth will fade, the radio signal will stop, the instruments will fall silent. The spacecraft will continue. This future gives the mission its emotional weight. While Voyager is alive, it is a scientist. After it falls silent, it becomes an artifact. The same object changes meaning without changing its path. It will no longer measure the plasma or count cosmic rays. It will no longer send its tiny stream of data home. It will become a frozen messenger drifting through the Milky Way. The golden record turns that future into something almost impossible to describe without emotion. Mounted on each Voyager spacecraft is a record created as a greeting from Earth. It contains sounds, music, images, spoken greetings in many languages, and information meant to describe our planet and our species. The chance that anyone will ever find it is incredibly small. Space is too vast. The probes are too tiny. Their paths do not aim directly at inhabited worlds. But the record was never only about probability. It was about meaning. It was humanity saying that if one of our machines enters the dark between stars, it should not go completely empty. The record carries oceans, thunder, birds, heartbeats, human voices, and music into a place where none of those things naturally exist. It is not a practical message in the normal sense. It is a symbolic one. It says that Earth was here. It says that a species looked up, understood that the stars were distant, and still chose to send a greeting. That may sound romantic, but it also connects directly to the science, because the same spacecraft that carries that message also measured the edge of our solar environment. It is both an instrument and a time capsule. It tells us what lies beyond the sun's bubble, while carrying a trace of the world inside that bubble. In one direction, it reports back to Earth. In the other, it carries Earth forward. This dual identity is part of what makes Voyager different from any ordinary probe. Most spacecraft are designed for a target. Orbit this planet, land on this moon, study this comet, return this data. Voyager had targets too, but after it completed them, its mission became open-ended. It was no longer about arriving at a place. It was about continuing until the spacecraft could no longer speak. That makes the mission feel like a slow fade rather than a final scene. There will probably not be one dramatic last image. There will not be a final photograph of the galaxy from outside the solar system. There will be a weakening power budget, a narrowing set of instruments, careful commands, and one day, no response. The last signal may be ordinary. That is what makes it more haunting. Space does not always give cinematic endings. Sometimes, the final moment is simply the moment a carrier tone never returns, or a spacecraft fails to answer a command sent from a planet it can no longer see. For the people who have worked on Voyager, that silence will be personal. For science, it will mark the end of a data stream from the only region of its kind we have ever measured directly. For the rest of us, it will mean that humanity's farthest active messenger has become a ghost ship. But even then, Voyager will not be gone, it will keep moving. This is another place where the story becomes almost impossible to hold in the mind. A spacecraft can die electronically and continue physically for billions of years, unless something destroys it. Space is not friendly, but it is also sparse. Micrometeoroids, radiation, and cosmic dust can slowly damage surfaces, but there may be no dramatic collision. The probe could drift through the galaxy long after every language on its record has changed beyond recognition. The sun will age, Earth will change. Human civilization may transform into something unrecognizable, or vanish, or spread, or fail. Voyager will still be traveling, A small object built by human hands will orbit the center of the Milky Way, not as a spacecraft under control, but as a relic sharing the sun's general galactic journey. That is terrifying in a quiet way. Not because Voyager is dangerous, because time is. The mission stretches our imagination in two directions at once. It shows us distance, because the spacecraft is far beyond the planets. It shows us time, because its future extends far beyond the mission, the engineers, the viewers, and perhaps the civilization that made it. It turns a scientific probe into a measure of human smallness, not by insulting us, but by placing us correctly against the galaxy. And still, the story is not only bleak. Voyager also shows what patience can do. A spacecraft that was never meant to last this long became a bridge between the planetary age of exploration and the interstellar age. It connected Jupiter's storms to the heliopause. It linked images of Saturn's rings to plasma waves between the stars. It turned a mission planned around a rare planetary alignment into one of the longest-running experiments in space history. That matters because exploration often begins with one goal and becomes something larger. When Voyager launched, the idea of crossing into interstellar space belonged to the distant future of the mission. The planets were the headline. Jupiter and Saturn were the promise. Uranus and Neptune were the bonus that made Voyager 2 legendary. But the long survival of both spacecraft allowed a new chapter to unfold. The spacecraft outlived the era it was built for. It kept going until the solar system itself became the subject. This is why the boundary matters so much. For centuries, humans looked at the planets and thought of them as the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Then we learned about asteroids, comets, Kuiper belt objects, dwarf planets, and the distant Oort cloud. Voyager added another layer to that picture. It showed that the sun creates a vast environmental bubble around all of these things. The solar system is not only a collection of objects orbiting the sun, it is a region shaped by the sun moving through the galaxy. That idea changes the scale of home. Earth is inside the magnetosphere. The magnetosphere is inside the heliosphere. The heliosphere is inside the Milky Way. And the Milky Way is moving through the cosmic web. Voyager lets us feel one step in that nested structure. It reminds us that home has layers we cannot see. We live inside protections and environments that are invisible until a spacecraft travels far enough to measure them from the outside. That is one reason the discovery feels eerie. The edge of the solar system was always there, but we only recently touched it. For almost all of human history, nobody knew there was a heliopause. People watched the stars, mapped constellations, built calendars, told myths, and wondered about the heavens. They did not know that the sun was surrounded by a vast magnetic bubble. They did not know cosmic rays were being partially filtered. They did not know a spacecraft would one day detect a boundary where particles from the sun give way to particles from the galaxy. The universe was not simpler before we understood it. We were just less aware of the complexity around us. Voyager expanded that awareness. It turned the outer solar system from a distant region into a measured environment. Now, when we say the sun protects us, it is not only poetry. It is measurable physics. The heliosphere reduces the amount of galactic radiation reaching the planetary region. It does not make space safe, and astronauts beyond Earth's magnetic field still face serious radiation risks, but it changes the conditions around the solar system. It is part of the background protection that makes our environment what it is. Outside that bubble, cosmic rays are more intense. Voyager found that directly. That fact gives the mission a practical relevance beyond wonder. If humans ever attempt true interstellar travel, they will have to deal with an environment not softened by the heliosphere. Spacecraft would need shielding, power, navigation, autonomy, and life support for durations that dwarf any mission we have attempted. The edge Voyager crossed is not just a scientific boundary. It is also a warning about what lies beyond any future human expedition. The galaxy is not designed for us. It is not hostile with intention. It is indifferent with physics. That distinction matters. Space does not hate life. It simply has conditions. Life must survive or avoid. Vacuum, radiation, cold, distance, time. When Voyager crossed into interstellar space, it entered a region where these realities become even more extreme in human terms. There is no planet nearby, no shelter, no sunlight strong enough to warm a habitat easily, no quick communication, no possibility of rescue. The spacecraft can survive because it does not need to breathe. Humans would face a different story. This is why Voyager is both inspiring and sobering. It proves we can send machines beyond the sun's bubble, but it also proves how hard the next step would be. Reaching interstellar space is not the same as reaching another star. Escaping the heliosphere is not the same as becoming an interstellar civilization. We have touched the edge, but not crossed the true ocean in any meaningful human timescale. And yet, touching the edge is not small. It is one of the greatest achievements in exploration. A tiny spacecraft reached a boundary larger than the planetary system, detected the galaxy beyond, and told Earth what it found. That is the central miracle of Voyager. Not that it traveled fast enough to make the stars accessible. It did not. The miracle is that it traveled far enough to reveal where the sun's immediate kingdom ends. And that revelation gives us a new way to think about every planet we have discussed in this channel. Every moon, every ring system, every comet and asteroid. They all exist inside this broader environment. Mars, Jupiter, Saturn, Neptune, Pluto, the Kuiper Belt, all of them are not just objects in orbit. They are objects inside the sun's moving bubble. Voyager looked back at that bubble from its edge, not with a camera, with instruments that counted the invisible. That is why this story belongs on Just About Space, because the most important space discoveries are not always the loudest. Sometimes they are quiet. Sometimes they are buried in data. Sometimes they come from a spacecraft so old that every command feels like a conversation across history. Now, let us return to the phrase in the title, 18 billion kilometers from Earth. For Voyager 2, that was roughly the distance when NASA announced it had entered interstellar space. For Voyager 1, the heliopause crossing was described at about 18 billion kilometers from the Sun. Either way, the number points to the same human feeling, a distance so large that Earth becomes less than a memory to the eye, a distance so far that the spacecraft's signal arrives faint, delayed, and precious, a distance where the solar system is no longer experienced as planets spread across the sky, but as a fading influence behind the spacecraft. The number is not only a measurement, it is a threshold. At that scale, the familiar solar system becomes abstract. The sun still dominates gravity, but not the surrounding plasma. The planets still orbit inside, but they are far behind. Earth still receives the signal, but only after hours of travel at light speed. The spacecraft still exists, but only as a point known through mathematics, radio tracking, and the patience of engineers. That is what distance does. It turns places into signals. It turns machines into coordinates. It turns a mission into a story told by delays. And Voyager's delay will only grow. Each year, the spacecraft moves farther away. Each year, the signal becomes weaker. Each year, power becomes more limited. Eventually, maintaining contact will no longer be possible. But until that day, the data remains unique. One of the most valuable things Voyager can still do is watch how conditions change over time in the local interstellar medium. It can detect plasma waves, measure magnetic fields, and track cosmic rays as solar disturbances move outward and interact with the region beyond the heliopause. This turns the mission into a kind of distant weather station, at the edge of the sun's influence. Not weather with clouds and rain. Weather made from charged particles and fields. A solar outburst can launch a disturbance that travels outward through the heliosphere. Months or years later, it may reach the distant boundary. It can cause plasma oscillations beyond the heliopause. Voyager can detect those oscillations, giving scientists a way to probe the density of the surrounding medium. In that sense, the sun sends ripples outward, and Voyager listens when those ripples arrive. The spacecraft is not just leaving the sun, it is helping us hear how the sun disturbs the galaxy around it. That sentence sounds almost impossible, but it is the essence of the interstellar mission. A star creates a bubble. A spacecraft crosses the bubble. Then the spacecraft watches the bubble interact with the galaxy from the outside. No telescope near Earth can fully replace that perspective. Telescopes can observe distant stars and infer that they may have astrospheres of their own. They can detect emissions and absorption features. They can study cosmic rays and interstellar gas from afar. But Voyager is physically there, sampling one location directly. It is not a complete map, but it is ground truth. Ground truth in a place with no ground. That is one of the most beautiful contradictions in space science. We need instruments at the place itself because remote observation can only tell us so much. We can model the heliosphere, but models need measurements. We can predict plasma behavior, but predictions need contact with reality. Voyager provides that contact, and every year it survives, that contact becomes more precious. The mission is now in a phase where the science is inseparable from the struggle to keep the spacecraft alive. Engineers must decide which systems matter most. They must preserve heat for components that were never expected to operate for half a century. They must manage an aging power supply and electronics exposed to decades of radiation and cold. The scientific goal is simple to say and difficult to maintain. Keep receiving data from a region no other human-made craft has reached. This is not glamorous engineering. It is careful, patient, and almost tender. A spacecraft cannot feel loyalty, but humans can feel it toward a spacecraft. Voyager has become a machine people care about, not because it is new, but because it endured. That endurance changes how the public sees it. We do not normally form emotional attachments to hardware, but Voyager is different. It carries the pale blue dot image in our memory, even though the cameras are long silent. It carries the golden record, physically. It carries decades of human effort. It carries the names of scientists, engineers, programmers, planners, and technicians, whose work still matters far beyond their original mission timeline. It also carries our sense of scale. When people hear that Voyager is outside the heliosphere, they sometimes say it has left the solar system. Scientists are more careful because the definition depends on what boundary you choose. If the solar system means the region where the solar wind dominates, then the Voyagers have crossed that boundary. If it means the region where objects remain gravitationally bound to the sun, then the Oort cloud may extend far beyond the spacecraft's current distance. By that definition, Voyager has not passed the outermost edge. This is not a contradiction. It is a lesson about definitions. The solar system has more than one edge. There is the edge of the planetary region. There is the Kuiper Belt. There is the distant realm of long-period comets. There is the sun's gravitational influence stretching outward into darkness. So when the title says, Voyager found something 18 billion kilometers from Earth, it is best understood as the edge of the sun's plasma bubble, not the final gravitational border of everything that belongs to the sun. That nuance makes the story better, not worse. A simple title opens a complex truth. The heliopause is the first major boundary where the sun's immediate particle environment ends. The Oort cloud, if we count it as part of the solar system, would be far farther away, perhaps extending thousands or tens of thousands of astronomical units. Voyager will not cross that region for a very long time. and it will be silent long before then. This gives the mission another strange feeling. The spacecraft has entered interstellar space in one sense, yet it is still traveling through the broader gravitational outskirts of the Sun in another. It has left the solar wind's domain, but not the Sun's story. The universe often works like this. Human categories are clean. Nature is layered. We want one edge, one border, one answer. Space gives us overlapping definitions, gradual transitions, and boundaries that depend on what you are measuring. Voyager found the edge that charged particles care about. Gravity tells a longer story. This layered understanding helps prevent one of the biggest mistakes in space videos, making the edge sound like a wall. The truth is more interesting. The heliopause is a pressure boundary. It is the place where the outward solar wind is balanced by the interstellar medium. It can move, it can ripple, it can leak, it can be compressed, it can be disturbed by events that began at the Sun. A wall is simple. The heliopause is alive with physics, and when Voyager passed through it, it entered a place that is still being interpreted. Scientists continue to analyze the data because the measurements do not only answer old questions, they create better questions. Why is the plasma just outside compressed? How porous is the boundary? Why are magnetic fields aligned the way they are? How do solar disturbances travel beyond the heliopause? What does the local interstellar medium look like on scales larger than the spacecraft path? These questions are not failures. They are progress. A good discovery does not end curiosity. It makes curiosity sharper. Voyager sharpened our questions about the Sun's place in the galaxy. Before the interstellar crossings, the heliosphere could feel like an abstract diagram. After Voyager, it became a real environment with measured transitions and surprises. It became something we know partly because a machine survived long enough to leave the main story and enter the epilogue. But Voyager's epilogue may become one of the most important chapters. That is a rare thing. Most missions end after their planned objectives. Voyager's planned objectives were extraordinary, but its unplanned longevity turned it into something larger. It became a mission about endurance. It became a mission about boundaries. It became a mission about how far human-made instruments can go before the universe becomes too distant for communication. And that last point brings us to the future. There will be a final day of contact. Nobody can name it with perfect certainty. It depends on power levels, instrument choices, engineering fixes, and the health of systems that have already lasted far longer than expected. NASA may keep one or both spacecraft communicating into the late 2020s or possibly beyond in limited ways. But the power decline is unavoidable. The plutonium heat source weakens. Electronics require energy. Radio transmission requires energy. The spacecraft is not being defeated by one dramatic event. It is being slowly claimed by thermodynamics. That makes its survival more impressive. Every additional month is earned through engineering. Every additional measurement is a small victory over distance and age. The final contact will not mean the spacecraft has stopped existing. It will only mean we can no longer hear it. Voyager will continue along its path, carrying the record, the instruments, the old computers, the faded surfaces, and the marks of its journey. It will become unreachable in practice, though not gone in reality. There is something deeply strange about that. An object can remain in the universe but leave human experience. Once the signal ends, Voyager becomes like a bottle thrown into an ocean so large that the shore can never be seen again. We will know approximately where it is. We will calculate its path, but it will no longer answer. That silence will complete the transformation from spacecraft to relic. And in the far future, if some intelligence ever found it, they would not find a working probe. They would find an object from a dead or transformed era of Earth. The record might be damaged, but perhaps still decipherable. The diagrams might still show the location of the sun relative to pulsars, though pulsars themselves change over time. The materials might still carry evidence of human manufacturing. The craft would be a fossil of technology. A fossil, not buried in rock, but moving through the galaxy. The chance of discovery is tiny, yet the possibility gives the mission a mythic shadow. Voyager is not aimed at an audience. It is sent into possibility. That is the deepest emotional truth of the Golden Record. It is not a practical letter with a guaranteed recipient. It is an act of cosmic imagination. It says that even if the galaxy is too large, even if the distances are cruel, even if no one ever hears us, we still chose to speak. And that brings the story back to what Voyager found. It found that the edge of the solar system is not the end of space. It found that beyond the sun's bubble, the galaxy is present in particles, plasma, fields, and radiation. It found that the shelter around us is real, but limited. It found that leaving the heliosphere is an achievement and a reminder of how much farther true interstellar travel would require. It found that space between stars is not empty, yet it is lonely beyond human intuition. And maybe most importantly, it found that our machines can survive long enough to discover things their creators could only hope for. That final idea is worth staying with. Voyager was not built by a civilization that already knew how to cross the galaxy. It was built by a civilization just beginning to send robots to other worlds. It used gravity assists, careful trajectories, radio communication, nuclear power, and extraordinary planning. It did not rely on impossible engines or fictional shortcuts. It reached interstellar space through patience. That is why the mission feels honest. It does not pretend the stars are easy. It proves that the first step is possible. The first step took decades. The second step may take centuries. The step after that may require technologies we have not invented, societies stable enough to plan beyond human lifetimes, and a willingness to accept that interstellar exploration is not a sprint, but a civilization-scale project. Voyager is the seed of that idea. A small machine left the planets and told us what waited at the edge. Now the question belongs to us. Will we ever build something that can go farther, faster, and with purpose toward another star? Will future probes carry instruments designed specifically for interstellar space instead of arriving there as a bonus after a planetary mission? Will humans remain inside the sun's bubble forever, sending only machines beyond it? Or will the heliopause one day become not the farthest boundary we have crossed, but the first boundary every interstellar traveler must pass? Voyager cannot answer those questions. It can only keep moving. And maybe that is enough, because every second it increases the distance between itself and home. Every day it travels farther into a region that once belonged only to theory. Every year it reminds us that the sun's influence is vast, but not infinite. Every signal it sends back is a message from the edge of the familiar. The terrifying part is not that Voyager found monsters. It did not. The terrifying part is that it found scale. It found a border so far away that it took a human lifetime to reach. And beyond that border, it found the beginning of distances so large that the journey had barely started. This is the true discovery. At 18 billion kilometers, Voyager did not find the end. It found the first proof that the end we imagined was only a beginning. The sun's bubble ended, the galaxy opened, and the spacecraft kept going. That is why Voyager's story remains one of the most powerful in space exploration. It is not only about technology, it is about perspective. We sent a machine to the planets, and it taught us where the sun's reach fades. We built it for a rare alignment of worlds, and it became a messenger between the solar system and the galaxy. We expected a mission, and we received a legacy. So when you think of Voyager now, do not imagine it as a bright spacecraft racing past planets with cameras clicking. That part happened long ago. Imagine it as something quieter, a small, aging machine in the dark, a radio signal thinner than a whisper, a nuclear heart slowly cooling, instruments listening to plasma where no human has been, a golden record fixed to its side, the sun behind it, no longer a blazing disk, but a bright star among many, Earth hidden completely, yet still waiting for each faint transmission. That is what Voyager found 18 billion kilometers from Earth. It found the edge of the sun's protective bubble. It found the pressure of the galaxy beyond. It found that interstellar space is not empty, not simple, and not close to anything we can easily reach. And it found that even when a spacecraft crosses the boundary of home, the universe ahead remains almost unimaginably wide. Maybe that is why the mission feels so haunting. Voyager gave us a victory and a warning in the same journey. The victory is that we reached the edge. The warning is that the edge is nowhere near the stars. For now, the spacecraft continues into the dark, carrying its instruments, its record, and its history. One day, the signal will stop, but the path will continue. Long after the last data point, long after the final command, long after Earth has lost the ability to speak with it, Voyager will still be out there. Not waiting, not searching, simply moving, a silent proof that something from Earth crossed the boundary